Alrighty, so today we're getting close to the end of the chapter. We're going to study the ambiguous case. So remember what I said yesterday, we cannot prove two triangles are congruent by angle side side. And this is the reason why we're going to see what happens here. See, the key here concept is that if you work with these two angles, which are supplementary, the sine of 32 degrees, if you make a sketch of the 32-degree angle here in quadrant 1, it's going to be positive, whatever that number is. But if you make a sketch of the quadrant 2 angle, the 148-degree angle, that actually is a supplementary 32. So how would you have found the exact value of the sine of 148 degrees? Well, you would have taken 180, subtract 148, and calculate the reference angle, which is the same as the 32. That answer is also positive because in quadrant 2, sine's positive. So hence, when we use the law of sines and we have a situation, we have the two sides and an angle, we might pick up an angle measurement that we're not sure which one to keep. So we may have to keep them both. Hence, we call it the ambiguous case. So there's a couple different kinds of questions they might ask us. They might ask us, first of all, find the two solutions. So they know there are going to be two separate triangles, totally non-congruent to each other, okay? So those are the kinds of questions oftentimes IB likes to ask. They're very lengthy, however, lots of work with law of sines, but the idea here, make a sketch of a triangle. Remember, the lower cases are the sides, so side A is 7.4. Side B is 18.1, and angle A here is 20 degrees. Okay, now I'm pretty much assuming that this is the smallest angle since 7.4 is a lot smaller than 18.1. So it does spell the naughty word, so we're going to use the law of sines. So 7.4 over the sine of 20 degrees is equal to 18.1 over the sine of angle B. So we cross multiply, we end up getting here the sine of angle B is equal to 18.1, the sine of 20 degrees. They have to get multiplied together and divide by 7.4. Now I'm going to write down the decimal that I get here on the calculator. I'm not going to round yet. No, let's not do that. But once again, on the graphing calculator or scientific calculator, make sure the mode is in degrees. Just double check, you never know if maybe someone borrowed your calculator. So 18.1 times the sine of 20 degrees, and we're going to divide that by 7.4, and the decimal we get is this big long decimal, so I'll write it all out here. 0.836562783. Okay, so now we want to find the measurement of that angle B. So if we hit second sine, second the negative sign. So don't risk making a typographical error. Just use the ANS feature and voila, we get 56.8 degrees. So angle B is about 56.8 degrees, we think, right? But here's the dilemma we face. What if this is actually the reference angle of the true answer? Isn't it conceivable that this angle B maybe is not acute, but in fact it's an obtuse? So that means, I better draw my second triangle, angle A, B, C. Use the same givens. Angle A is 20 degrees. Side A is 7.4, side B is 18.1, but now we have two possible answers. So maybe angle B here is 56.8 degrees, or maybe perhaps it's the supplementary, 180 minus 56.8, and the answer, oh dear, okay, so what if it is 123.2 degrees? It's possible, right? If you take the sum of those two angles, it's still less than 180, likewise up here. So now, as you can see here, these are two non-congruent triangles. And if this doesn't convince you, maybe nothing will convince you, but you're not supposed to use angle side side to prove two triangles are congruent from Common Core geometry. Finish up the problem. I'm just going to add these two angles up and subtract from 180 to find the measure of angle C. No point in using law of sines. In fact, I don't think you can. There's not enough information. So 20 plus 56.8. I'm going to subtract that sum of 76.8. Oh, okay, so this implies then angle C is the obtuse angle of this triangle, 103.2 degrees. Whereas over here, it's obvious you can only have one obtuse angle in a triangle. So if I add those up, I'll get 143.2. So if I subtract that from 180, that angle is 36.8 degrees. So both triangles' angles are solved. The only thing that's left now is if we're asked to find the two solutions of the triangle, we need to make sure all the sides are found. So in this case here, this top problem, I'm going to use C over the sine of the obtuse angle I found here of 103.2 degrees. And I'll probably just use the 7.4 over the sine of 20. Whereas down here, I'm going to still use a 36.8 to find side C, but you're going to get a different answer. Sine of 36.8 degrees is equal to 7.4 over the sine of 20. I mean, you could, yeah, obviously you could argue these are the same ratios, but these two angles have nothing in common. So you're going to get two different lengths for side C. So this top triangle here, the side C will be whatever 7.4 times the sine of 103.2 degrees divided by the sine of 20, whereas this triangle, side C, will be whatever 7.4 times the sine of 36.8 degrees divided by the sine of 20. So you're going to get two slightly different answers here. So in this case here, if I go to the calculator, 7.4 times the sine of 103.2 and divide by the sine of 20. Side C is about 21.1 on the top triangle. Or the bottom triangle, if I calculate that, 7.4, the sine of 36.8 degrees divided by the sine of 20. I get, this is an interesting one. Just a reminder, when you do 3 sig figs, the 6 rounds the 9 up, which rounds the 12 up, so your answer for side C here is actually 13.0. That's probably as difficult as this could possibly be here, really exploring the law of sines a little bit more in depth. Okay. Now, sometimes the triangle questions aren't as bad. Sometimes it's a matter of how many triangles can be formed. So you draw a picture, label the information. So here, suppose side A is 4, so I'll label side A 4. Side B is 6, label, and okay. Now the measure of angle A is 150 degrees. I'm pretty sure I took this from an old practice SAT. Some of you can see right away there's no possible triangles here. But let's use the law of sines. I can convince you this way also. 4 over the sine of 150 degrees is equal to 6 over the sine of angle B. So we cross multiply. We're going to find the decimal. The sine of angle B will be equal to 6 times the sine of 150 degrees divided by 4. So what decimal do we get here? All right. So 6 times the sine of 150 degrees divided by 4. So here's the decimal I get. I get 0.75. Wait a minute, for real? Just making sure I didn't type anything wrong. No, I guess I did. So far so good. It's within the range of the sine curve. Remember, -1 to 1. So, okay, so far so good. Second sine, type in that 0.75. The angle get is about 49 degrees. Let's just approximate. It's not a matter of solving triangles, it's a matter of determining how many triangles. Now stop, think for a moment. Does it make realistic sense? Can you really have another angle 49 degrees in this triangle? No. So again, the triangle inequality you learned in Common Core geometry, that if this is the largest angle, obviously, then the side opposite should be the longest. 6 is bigger than 4. So that's how I think problems like this come up on the SAT, because it goes back to Common Core geometry. But using law of sines, there are no triangles. Okay. Now I have another practice here. I switched it up. What if I make A the 4 and side B the 6, and this time make angle B 150 degrees? So we do the same thing, but now 6 on top of the sine of 150 degrees is equal to 4 over the sine of angle A. We see here that the sine of angle A will equal 4 times the sine of 150 degrees divided by 6. So let's see what decimal we get here. If this decimal is bigger than 1, forget about it. That's another throw it out. No, not possible. I think this one's gonna work, but let's just double check. 4 times the sine of 150 degrees divided by 6. Okay, I get 0.3 repeating as my decimal. Okay, 0.3 repeating. So now if I go to my calculator once again, second sine, second answer, I get about 19 degrees. Okay, so angle A is about 19 degrees. Now, let's go back to the picture here. It's okay to have a 19-degree angle in this triangle. Yeah, 19 plus 150 is 169. It leaves 11 degrees for angle C, so it is possible. But, like question number 1, how do you know you're going to have a second triangle? Well, this is what I would do. I would redraw the picture. Okay, so angle A is down here, right? A, B, C. Use the same givens, the 4, the 6, and the 150. So instead of labeling this a 19, use the supplementary angle. So supplementary angle, remember, 180 minus 19. Okay, so the question is, could angle A be 161? And that's a dead no, because you already exceeded 180 degrees. That's the limit of how many degrees are in a triangle. So in this example, only one triangle exists. I like these questions because, as you can see here, we're not left finding the rest of the triangle information. It's just a matter of reasoning how many possible triangles could there be. Okay. That pretty much summarizes what we have new for today. So in summary, we could either be asked how many triangles are formed, which is my favorite, or we could be asked to solve both triangles. So it's implied that when you find the supplementary angle, it's going to work and you'll have the second non-congruent triangle. I know there's an exit ticket here. I'm gonna go ahead and solve that, and I'll submit the notes for today, as well as the answers to yesterday's and today's homework. So we're getting close to the end of this unit. Yeah, all we have left are the word problems. And they do get kind of intense, but I kind of scaled it back since we're on this remote online learning. So that pretty much completes the course as of Monday. And I'll give you another take-home quiz to finish off your averages for quarter 4. Thanks. If you have any questions, just let me know. Great. Thanks.